Hello friends, today we are going to see the trick by which we can solve any sinusoidal state analysis based sum very fastly, very easily. Okay, so before we jump to the sum, first let us see how to judge whether our sum is for sinusoidal state analysis or not. Okay, so for that you have to check your input. Okay, if your input is in the form of sinusoidal, then it means that this sum is for sinusoidal state analysis. Okay, so now we know how to judge whether our sum is for sinusoidal state analysis or not. Okay, so now let's jump to the sum. This sum is from EC 2004 and the question says that the circuit shown in the figure with R is equals to 1 by 3 ohm, L is equals to 1 by 4 Henry, C is equals to 3 Farad has input voltage V of t is equals to sin 2t, and we have to calculate the resulting current I of t. Basically we have to get our I of t and V of t is present here. Okay, if you see the question carefully, here you have V of t is equals to sin 2t, which means our input is in the form of sinusoidal. Okay, that means that we have to do the sinusoidal state analysis here. Okay, and these are the options from which we have to get the correct one. Okay, so let's see the trick. The trick says that you have to follow these three steps. Okay, so the first step says that you have to keep input and output as it is. Okay, so it is saying that if your input is in the form of sinusoidal, keep as it is. Okay, you are not required to do anything with your input as well as your output. Okay, now the second step says that you have to change all other element, basically element apart from your input and output, to its Laplace domain and then get the reactance form. Okay, so basically you have to convert all other element apart from your input and output into its Laplace domain, then you have to get the reactance from that. Okay, to get the reactance you have to just substitute s to j omega. Okay, and then you will get the reactance. Okay, and last step is that you have to solve it considering your basic network sum. Okay, once your network is converted into reactance, then just you have to consider that as your basic network and solve it. Okay, so now let's apply this trick to get our answer very fastly. Okay, so this is the circuit. First step says that we have to keep input and output as it is. Okay, we have to calculate I of t and V of t was given, so we will keep I of t and V of t as it is. Okay, basically we have not touched input and output. Okay, now the second step says that we have to change all other element apart from our input and output to its Laplace domain. Okay, so if we convert R to Laplace domain, it will be R itself. If we convert L to Laplace domain, it will be SL, and then if we convert C to Laplace domain, it will be 1 by SC. Okay, here in the question L is given as 1 by 4, so it will be 1 by 4s. SC is given as 3 Farad, so it will be 1 upon 3s. Okay, now once you have converted into Laplace, then you have to get your reactance, and to get reactance we will just substitute S to j omega. Okay, now once we have converted to reactance, then just we have to simply solve the circuit considering it as basic network. Okay, now in the question we have to get I of t. Okay, to get this I of t we are going to apply node at this point. Okay, if you apply node at this point, we will have minus I of t plus V of t by R plus V of t by SL plus V of t upon 1 upon SC. Okay, so this is what I have written here. Okay, since I have already told you, you have to get your reactance form once you have converted to Laplace domain. Okay, since in this circuit I have not done that, but I recommend you to do that. Okay, so here if you simplify this equation, we will have I of t equals to V of t in bracket 1 upon R plus 4 by S plus 3S. Okay, here you can see, here I have not converted S to j omega, and I am doing that in the third step. Okay, so you can see I am wasting one step here. Okay, instead of doing this, we will get the reactance form in the circuit itself. Okay, so if we put S equals to j omega, we will get I of t is equals to V of t 1 upon R. This S will be substituted with j omega, so it will be 4 upon j omega plus 3 j omega. Okay, so this is our first equation. Okay, now from the input you can see that we have an input of V of t is equals to sin 2t. Okay, if you compare this with sin omega t, you will get to know that your omega is equals to 2. Okay, so you have to simply substitute your omega equals to 2. Okay, so if you substitute that, you will get 3 plus 4 by j2 plus 3j into 2. Okay, now you have your it is equals to sin 2t 3 minus 2j. Here you can see if we take j into the numerator, we will get minus 4j by 2. Okay, so it will be minus 2j. Then here we will have 3j into 2 is equals to 6j. Okay, if we simplify it, we will get sine 2t multiplied by 3 plus 4j. Okay, note one thing here, I'm not doing anything with the input. Okay, I'm keeping as it is. Okay, so once you have arrived on this step where you have your complex number with your input, now just you have to get the magnitude as well as angle of your complex number. Okay, if you calculate the magnitude of this complex number, it will be under root of 3 ka square plus 4 ka square, basically real part ka square plus imaginary part ka square. It will be 9 plus 16, it will be under root of 25, which is 5. Okay, so this is our magnitude. And then if you calculate the angle, it will be tan inverse of imaginary by real. Okay, so it will be tan inverse by 4 by 3, where we know that tan inverse of 4 by 3 is 53.13. You can calculate this in the calculator itself. Okay, so you have to multiply your magnitude with your input magnitude. Okay, so 5 into 1, it will be 5 itself, and angle you have to add with omega t. Okay, so our answer will be 5 sine 2t plus 53.13 degree. Okay, so here you can see this is our magnitude and this is the angle. Okay, so you have to just multiply the magnitude with the input magnitude and add your angle with the input omega t. Okay, so this is our final answer. Okay, and if you check from the option, you can clearly say this A option is the correct one. Okay, so in this sum, what we have done, we have followed all three steps. We have kept input and output as it is. We have changed all the other elements into its Laplace domain. Then we have taken the reactance form. Okay, once the circuit is in the form of reactance, then we have just considered that circuit as our basic network, and we have used our simple KCL, KVL to get our answer. Okay, so this is the correct answer. Okay, now let us see the second sum. This second sum says that in the RLC circuit shown in the figure, the input voltage V of t is given by. Okay, so here there is a twist. VIT is now having a two input. Okay, which is 2 cos 200t plus 4 sin 500t. Okay, and we have to get the output voltage V of t. Okay, so this is our input, this is our output, which we have to calculate. Okay, and this is the option. Okay, in this sum only we will get to know the importance of converting into the reactance form in the circuit itself. Okay, so as we have decided, we are going to follow that three step. Okay, but before that you have to see this. Here we have two input. Okay, you can see that here we have 2 omega. Okay, so we have two different AC input voltage. Okay, which is 2 cos 200t with the omega equals to 200 and 4 sin 500t with the omega is equals to 500. Okay, so to solve this type of sum, you have to use superposition theorem. Okay, so you have to consider one input source at a time. Okay, so now let us consider that 2 cos 200t is active. Okay, so basically our omega is 200 for now. Okay, so as we have already decided, we will keep VIT, VOT as it is. Okay, we are going to change only the other elements such as R, L, C. Okay, so R will be as it is. We have to convert L and C. Okay, let's say this is L1, let's say this is C1, this is L2 and this is C2. Okay, so we have to convert into Laplace domain. Okay, so this L will be converted into SL, this C will be converted into 1 by SC. Okay, and then we have to get the reactance. Okay, for inductor the reactance is XL, for capacitance the reactance is XC. Okay, as we convert L to SL, it will be SL, then we have to substitute our S to J omega, so it will be J omega L. Okay, so this is our XL. Okay, XL is basically omega L. Okay, now if we convert C to Laplace domain, it will be 1 upon SC. If we substitute S to J omega, it will be 1 upon J omega C, and apart from this J, whatever thing is, it is your XC. Okay, so XC is 1 upon omega C. Okay, so now if we get the reactance of inductor and capacitance, we will get reactance of inductor 1, it will be XL1, which will be omega L1. Omega is 200, so it will be 200 into L1 value is 0.25, which is 1 by 4, so it will be 50. Okay, similarly if we calculate XC1, it will be 1 upon omega C1, which is equals to 1 upon 200 into 100 into 10 raised to minus 6. Okay, so if we simplify it, we will get 10 raised to 6 upon 200 into 100, so it will be 10 square upon 2. Okay, so it will be 50. Okay, so we get our XL1, we get our XC1. Okay, now let us find the reactance of XL2 and XC2. Okay, so XL2 will be omega into L2, So it will be 200 into 4 by 10. So it is 80. XC2 will be 1 upon omega C2. 1 upon 200 C2 value is 10 microfarad. Okay, so it will be 10 into 10 raised to minus 6, which will be 10 ka cube upon 2. So it will be 500. Okay, so we have successfully got the reactance of all inductor as well as capacitor. Okay, now let's see the magic. Okay, so once you have get all this reactance, okay, you have to just substitute that into a circuit. Okay, so here you can see this is your modified circuit where your SL is converted into J omega L, which is J into XL. Okay, so it will be J into 50, and similarly your capacitor will be minus J50. As you can see here, you have 1 upon J, so it will be minus JXC. Okay, so here you have minus J50, and then this resistor will be as it is. Here you will have J80, here you will have minus J500. Okay, so if you observe this circuit carefully, here we have J50 minus J50. Okay, since this is in the form of reactance, we can add up directly. So it will be J50 minus J50, it will be 0 ohm. Okay, so 0 ohm, it means that short circuit. Okay, and since here this 2 ohm and this short circuit is in parallel, so 2 ohm multiplied by 0 upon 2 ohm plus 0, it will be 0 itself. Okay, so basically this whole reactance is converted into short circuit path. Okay, if you see this modified circuit carefully, here you have VIOT, then you have a short circuit path, then you have this branch, and then you have your output voltage VOT. So from this we can say that this VOT will be equals to VIT since it is directly connected. Okay, so for this it will be VOT is equals to VIT 2 cos 200t. Okay, so even if you calculate this thing, you can get your option. As you can see, only B option satisfies that you have your output as 2 cos 200t. Okay, so even if you calculate this first thing, you can get your answer. But let us see the other part also. Okay, so the other part is you have to deactivate this input and you have to activate this. Okay, so if we activate this, so here for this we will get our omega as 500. Okay, so similar thing we are going to do now. Okay, first we are going to convert to Laplace domain, then we will get the reactance. Okay, so reactance will be XL1, which will be omega L1. Omega is 500 here, L1 is 1 upon 4, it will be 125. Okay, similarly XC1 will be 1 upon omega C1, which will be 20. Okay, XL2 will be omega L2, which will be 200. XC2 will be 1 upon omega C2, which will be 200. Okay, now if you substitute all this value into the circuit, you will get J125 minus J20, 2 ohm, J200 minus J200, and then this is your R, which is 2 ohm. Okay, now if you observe this circuit carefully, here you have J200 in parallel with minus J200. Okay, if you calculate the parallel equivalent of this, it will be J200 parallel with minus J200, it will be J200 multiplied by minus J200 upon J200 minus J200. Okay, so this will be 0. Okay, anything by 0 it will be infinite. Okay, and infinite ohm, it means that this part is open circuited. Okay, so our modified circuit will be somewhat like this. Okay, this is our Z1, basically this is our one reactance, then we have our open path, then we have this R. Okay, so here you can see we don't have any closed paths, it means that your current will be 0. Okay, so whatever your input is, your output will be same. Okay, so VOT will be VIT itself, which will be is equals to 4 sin 500t. Okay, so if you see the option, we have our output voltage VOT as 2 cos 200t plus 4 sin 500t is similar to the input. Okay, so our output voltage is equals to input voltage. Okay, so this was the second sum. So from this second sum, we have learned that we have to do all the conversion into the circuit itself. Okay, we will convert to Laplace domain, we will find out the reactance value, then we will substitute the reactance value in the circuit itself, and after that only we are going to start solving. Okay, so this will make our simplification more easier and we will get the answer very fastly. Okay, so we have seen the sum where we have 1 omega, where we have 2 omega. Okay, but if in case we have a DC source along with the AC source, then what we have to do? Okay, so then also we have to use SPT. Okay, but to get the steady state value when DC source is present, then you have to get your I infinity or V infinity. Okay, let's say this is the circuit when your DC source is active and you have to get your VCT. Okay, so to get VCT, we are going to use the T equals to infinite period for DC source. Okay, so if we use T equals to infinite period, it means that we have to open circuit the capacitor and short circuit the inductor. Okay, so it will be 5. These are and here we have open circuited R capacitor. Okay, we have to get this VC infinite. Okay, so from this circuit you can see that your VC infinite will be simply 5 volt. Okay, so you get your VC infinite as 5 volt and your IC infinite is 0 ampere, and note this thing, this is your steady state value. Okay, so you have completed your DC part, then you have to go for your AC part. Okay, so you have seen for 1 omega, for 2 omega, for DC source with. Hello friends, today we are going to see the trick by which we can solve phasor based AC circuit sums very easily, very fastly. Okay, so before we move to the sum, let us see the basic concepts that are required to solve sum. Okay, so let's start with the series RLC circuit where you will find R, L, C all connected in series. Okay, so this is the voltage source which we have applied across this RLC. Okay, so this voltage source across this RLC combination will be VR plus JVL minus JVC. Okay, now you may be wondering how this equation come. Okay, so to understand this, let us find out the input impedance of this network. Okay, and to get the input impedance, we have to convert this circuit into the reactance form. Okay, so to do that, we are going to convert all elements into reactance form. R will be R only, L will be SL. Now you will substitute S to J omega, so it will be J omega L. Okay, similarly, C will be converted to 1 upon J omega C. Okay, now since this network is converted into reactance form, we can get the input impedance very easily. Okay, so this input impedance will be Z equals to R plus J omega L plus 1 upon J omega C. Okay, now if you multiply this equation with I, it will be IZ plus IR plus J I omega L plus 1 upon J omega C into I. Okay, now if we take J to numerator, we will get minus J I upon omega C. Okay, now if we try to simplify this, I into Z, it will be Vs, right? Input current into input impedance, it will be Vs, right? Input voltage, so it will be Vs equals to VR. Why? Because you can see I multiply by R, it will be VR, right? Plus J I into omega L, I into reactance of inductor, it will be VL, right? I into R is V, right? So it will be JVL. Similarly, for capacitor, it will be minus JVC. Okay, the reactance of capacitance is 1 upon omega C, so it will be I into R, so it will be in voltage form. Okay, so minus JVC. So this is the equation that we are going to use. Okay, so this is Vs equals to VR plus JVL minus JVC. Okay, now if we simplify this equation, we will get VR plus JVL minus VC. Okay, basically we are clubbing real part and imaginary part separately, so we will get VR plus JVL minus VC. Okay, so this equation is converted to A plus JB form. Okay, now you can get magnitude and angle very easily. Okay, so magnitude of Vs will be under root of VR square, basically real part ka square plus imaginary part ka square. So here it will be VR square plus VL minus VC the whole square. Okay, similarly our angle will be tan inverse of imaginary part by real. Okay, so it will be tan inverse of real minus VC upon VR. Okay, so this was the basic thing that you should know about series RLC circuit. Okay, similarly we have to understand the same concept for parallel RLC circuit also. Okay, so here you can see RLC all connected in parallel, and we have applied IS, basically input current, across this RLC parallel combination. Okay, so we will get IS equals to IR plus JIC minus JIL. Okay, so reason is you have to find out the admittance now. Okay, for parallel circuit you can find admittance very easily, and for series RLC circuit you can get impedance very easily. Okay, so in parallel we are finding admittance, so admittance will be 1 upon R. Basically you can say this is the impedance. Okay, so admittance will be 1 upon R plus 1 upon J omega L. Impedance is J omega L, so admittance will be 1 upon J omega L, right? Similarly for capacitor it will be 1 upon J omega C. Okay, so all are in admittance form. Okay, so this is our input admittance. Now if we multiply this complete equation by V, we will get Vy plus V by R minus J V by omega L plus J V omega C. Okay, so if you see carefully here, you have voltage upon impedance, right? Voltage into admittance is nothing but voltage upon impedance. Okay, so V by R is basically I, so all these terms are converted into I, so we will get IS, this is our input source, equals to IR, basically the current flowing through the resistor, minus J, you have kept J separately, so you have V upon omega L, which is nothing but IL plus JIC. Okay, so this is the equation that you should know about parallel RLC circuit. Okay, so if we simplify this equation, if we club real and imaginary parts separately, we will get IS equals to IR plus JIC minus IL. Okay, note this difference. Here you were having VR plus J VL minus VC. Here you have IS equals to IR plus J IC minus IL. Okay. Now if you find out the magnitude, it will be mod of IS equals to under root of IR square plus IC minus IL the whole square. Okay. And if we calculate the angle, it will be tan inverse of IC minus IL by IR. Okay. Now along with this, you should know about power factor. In all series circuit, the power factor is given by cos phi, which is R by Z. Okay. This R is your resistance and this Z your input impedance. Okay. Here the minimum value of Z is R. Okay. So we can say that R by R will be 1. Okay. And if we increase the value of R, as we know that minimum value of impedance is R. Okay. So if we increase our impedance greater than R, so this factor will be always less than equals to 1. Okay. So we can say that power factor will be always less than equals to 1. Okay. Now for parallel circuit like parallel RC, parallel RL, parallel RLC circuit, power factor is given by cos phi, which is equals to Z by R. Okay. So note one thing, for parallel circuit, this power factor is given by Z by R. For series circuit, it was R by Z. Okay. Here the maximum value of Z is R. Okay. So if we decrease the value of Z, so this factor will be less than 1 only. Okay. So we can say that power factor will always be less than equals to 1, whether it is for series or parallel circuit. Okay. So this was the basic concept that you should know before you solve the sum of phasor circuit. Okay. So let's start solving the sum. Okay, so this is the first sum from EC 2005. The question is given that for the circuit shown in the figure, the instantaneous current I1 is. Okay, so this is a circuit where you have to find out this I1. Okay, and the options are present here. Okay, very first thing that you should do about phasors, that you should convert all the elements into its reactance forms. Okay, so as you can see in this circuit, all the elements are already converted into reactance form, so we need not to do this step here. Okay, so once you have converted your circuit into reactance form, then you have to start solving your circuit considering that your basic circuit. Okay, so here in this circuit we have to get this I1. Okay, so if we apply KCL here, you can see the current flowing here, it is phi angle of 0 degree ampere. Okay, so here it will be minus phi angle of 0 minus I1 plus tan angle of 60 degree ampere. Okay, so I have applied the KCL at this node. Here the current was phi angle 0 ampere, here the current was I1, and here the current was tan angle 60 degree ampere. So we get this equation, minus phi angle of 0 degree minus I1 plus tan angle of 60 degree equals to 0. Okay, now if we take I1 on one side and rest of the thing on the other side, we will get I1 equals to tan angle 60 degree minus phi angle of 0 degree. Okay, now this is in the form of polar. Okay, if we have to convert this into exponential form, it will be 10 e raised to j60. Okay, so basically magnitude into e raised to j angle. Okay, so if we convert this into polar form, this will be 10 e raised to j60 minus phi e raised to j0 degree. Okay, now as we know, e raised to j theta is basically cos theta plus j sin theta. Okay, so we can write this equation as 10 into cos 60 degree plus j sin 60 degree. Similarly for this, it will be minus phi in the bracket of cos 0 plus j sin 0. Sin 0 is 0, so this term will be 0 only. Okay, so here we will get 10 cos 60 degree is 1 by 2 plus j sin 60 degree is root 3 by 2 minus 5 into 1, it will be minus 5. Okay, so here you can see 10 by 2 will be 5, so this 5 and minus 5 will get cancelled and we will have only this term 10 into j root 3 by 2. Okay, so this is our I1. I1 is equals to j 10 by 2 root 3. Okay, now if we write this into phasor form, it will be 10 by 2 root 3 angle of 90 degree. Okay, as you can see here, all the options are written in phasor form. Okay, so you have to convert your rectangular form to your phasor form. Okay, so it will be 10 root 3 by 2 angle of 90 degree ampere. Okay, so the correct option will be this A. Okay, now let's move on to the second sum. This second sum says that you have to find out the current I in the circuit, and note one thing, this is from EC 2010. Okay, the circuit is here, the options are here. Okay, so the very first step to solve this phasor based sum is you have to convert your circuit into reactance form. Okay, so L will be converted to j omega L, C will be converted to 1 upon j omega C, R will be R only. Okay, so if you observe this circuit carefully, here in the input voltage source, it is given that you have a voltage of 20 angle of 0 degree and omega is mentioned, which is 10 raised to 3 radian per second. Okay, we are going to use this omega to convert this L into its reactance. So L will be converted to j omega L. Okay, so j into 20 into 10 raised to minus 3 into omega. Okay, omega is 10 raised to 3. Okay, so if we convert this, it will be j omega L, j into 1000 into 20 into 10 raised to 3. So it will be j20. Okay, so this L is converted to j omega L, which is j20, and this c will be 1 upon j omega c. J into 1000 into c is 50 into 10 raised to minus 6. If you take 10 raised to minus 6 in numerator, we will get 10 raised to 6 upon 50. Okay, so if we simplify it, we will get minus j20. Okay, so this capacitor is converted to minus j20 and this L is converted to j20. Okay, now you can see all the elements are converted into reactance form, so we can get our answer very easily. Okay, so now we have to consider this network as our basic network and we have to apply KCL and KVL. Okay, so as we know, we have to get this I. Okay, so to get this I, we are going to apply the node. Okay, now this time we will consider the voltage at this node. Okay, so here we will have V1 minus 20 angle of 0 degree upon reactance. Okay, reactance is J20 plus V1 by 1 plus V1 upon minus J20. Okay, so this is what I have written here. Okay, now if we take V1 on one side, we will get V1 in bracket 1 upon J20 minus 1 upon J20. Okay, plus 1 is equals to this term. It will be 20 angle 0 upon J20. Okay, this minus will be converted to plus as we take this term to the other side. Okay, so now if you try to simplify it, you can see this term and this term will get cancelled and you will have 1 into V1. So it will be V1 equals to this 20 gets cancelled. You will get 1 angle of minus 90 degree. As you can see, if we take J to numerator, you will have minus j. Okay, and minus j we can write in the form of angle, it will be minus 90 degree. Okay, so you get your V1 equals to 1 angle of minus 90 degree. Now this is not our answer, we have to find out this I, right? As you can see, we are asked to find out this I, so I will be this V1 by 1. Okay, so V1 by 1, it will be 1 angle minus 90 degree only. Okay, now if you see the option, you can see we have options in J form. Okay, so to convert this answer into J form, it will be minus 90 will be converted to minus J. Okay, so the answer is minus J 1 ampere. Okay, so you can see how easily you are solving AC circuit sums. Okay, now let's move ahead to the third sum. So this third sum is from EC 2012 and the sum is in the circuit shown below. The current through the inductor is, okay, basically we have to find out the current through this inductor. Okay, so IL we have to find out. Okay, and the options are present here. Okay, so if you see this circuit, you may be wondering this is very complex, but let me tell you, this is not complex as you think. Okay, we have to get this IL. Here you can see we have the current. Okay, the current through this branch is 1 angle 0 degree ampere. Okay, so if we apply KCL at this node, we have to find out the current IL. This is 1 ampere, so this current must be IL minus 1. As you can see, if we add IL minus 1 plus 1, it will be IL, right? So now we know this branch current, this branch current. Okay, now let's see whether we can apply KVL or not. Okay, so you can see we know this branch current, we know this resistance. Okay, here we don't know the current, here we don't know the current, here we know the voltage, here we know the voltage. Okay, now if we apply KVL like this, okay, in this bigger mesh, we will get IL J1 ohm minus 1 angle of 0 degree plus 1 angle of 0 degree plus IL minus 1. Okay, so this is what I have written here, minus 1 angle of 0 degree plus 1 angle of 0 degree 1 into IL minus 1 plus J into 1 into IL. Okay, so this is our first equation. Now if we try to simplify it, if we try to get IL on one side, we will get IL 1 plus J. Okay, and here you can see this term got cancelled and we have only this. Okay, so if we take on other side, it will be equals to 1. Okay, so we will get IL equals to 1 upon 1 plus J ampere. Okay, so this is the answer. Now if you compare with the option, you can see this C is the correct answer. Okay, so from this sum, what you get, the circuit may be complex, but it is not the case that always your solution will be complex. Okay, so it's on you how you use KCL and KVL to get your answer. Okay, now let's move ahead to the fourth sum. This sum is from EC 2015. The question is the voltage VC across the capacitor in volts in the network shown is. Okay, now if you see this network here, you have a series RLC circuit. Okay, where you have this VS, this is a VR, VL, and you have to find out this capacitor voltage. Okay, as we have seen in the basic concepts, we are going to use the same equation here. Okay, as we have seen, VS is VR plus JBL minus JVC. Okay, note one thing, this is not the resistive network, okay, where you will find the sum of all the voltage to be 100 volt. Okay, most of the students do a mistake where they try to make this capacitor voltage such that they will get 100 volt. Okay, and they end up with 80 plus 40 is 120. Okay, so they end up with minus 20 volt as their answer. Okay, but note one thing, this is not your resistive network, this is a complex network. Okay, so for that you have to use this equation where you will have Vs equals to Vr plus JVL minus JVC. Okay, now if we club real and imaginary part, we'll get Vr plus JVL minus Vc. Okay, so our magnitude will be Vs equals to under root of Vr square plus Vl minus Vc the whole square. Okay, Vr is 80, so it will be 80 ka square, plus Vl is 40, so it will be 40 minus Vc the square. Okay, here we have Vs as 100 volt. Okay, so we have to make LHS equals to RHS. Okay, so for that here you can see 80 ka square, it will be 6400. Okay, and to get this 100 we should get this term as 10,000. Okay, so here we have 6,400, so this term must be 3600. Okay, such that we will get 10,000, and 10,000 ka under root is 100, right? So 40 minus Vc the whole square must be equals to 3600, right? So if we take the under root, we will get 40 minus Vc is equals to plus minus 60. Now if we solve this, we will get Vc is equals to 100 volt and minus 20 volt. Okay, out of this we have to get one answer. Okay, so let me tell you, Vr, Vl, Vc, all these terms are positive real number. Okay, so the correct answer will be Vc is equals to 100 volt and not minus 20 volt. Okay, so note this step, you have to take Vc, Vr, Vl all positive real number. Okay, so our correct answer will be Vc is equals to 100 volt. Okay, now let's move on to the last sum. This sum is from EC 2017. The question is the positive angular frequency omega in radians per second at which the magnitude of the phase difference between the voltage V1 and V2 equals to pi by 4 radians. Okay, so here we have to calculate omega, and we are given with that the angle between V1 and V2 is pi by 4. Okay, so here also we will use the same procedure, that first we will convert all the elements into its reactance form. Okay, so we will get this circuit. Here you can see 100 cos omega t, this is your input, 1 ohm, j omega 1. Okay, so if you observe the circuit carefully, here you can see your input voltage is 100 cos omega t. Okay, which is a sinusoidal input. Okay, so it means this sum is of sinusoidal state analysis. Okay, if you have to do this sum by phasor, you have to convert this 100 cos omega t into 100 angle of 0, and then use the same procedure that I have taught you in the above sum. Okay, but let me tell you, by this you will make your sum very complex. Okay, so it's better that whenever you get 100 cos omega t, basically whenever you get a sinusoidal input, you use your sinusoidal state analysis steps. Okay, so the first step was that you have to keep your input and output as it is. Okay, we will keep input and output as it is. Okay, we will convert all the elements to its reactance form. Okay, that we have done in the circuit itself. Okay, now we have to consider this circuit as our basic network, and we have to use KVL KCL to solve this sum. Okay, so here you can see we have to get this V1 and V2. Okay, so for V1 we will use the voltage divider rule. Okay, so our V1 will be 1 upon 1 plus j omega plus 1. Basically this resistance upon this resistance plus this. Okay, so you will have 1 upon 2 plus j omega into your input. Okay, this is your input, 100 cos omega t. Now if we simplify this, if we take magnitude and angle of this, it will be 1 upon under root of real part ka square, it will be 4, plus imaginary part ka square, it will be omega square, angle of tan inverse of omega by 2. As you can see, imaginary is this, real is this. Okay, so angle will be tan inverse of omega by 2. Now as we have seen in the sinusoidal state analysis video, always we have to add this angle into our input. Okay, and we will multiply our magnitude with the magnitude of our input. Okay, so our total magnitude will be 100 upon under root of 4 plus omega square cos omega t, and if this angle goes in numerator, it will be minus tan inverse of omega by 2. So if we add that, we will get cos omega t minus tan inverse of omega by 2. Okay, so this is our V1. Okay, now similarly if we calculate for V2, V2 will be 1 plus j omega upon total reactance, so it will be 1 plus j omega plus 1, so 2 plus j omega into input. Okay, so if we take magnitude and angle, it will be under root of 1 plus omega square, and angle, it will be angle of tan inverse of omega by 1. Okay, imaginary is omega, real part is 1. Okay, so it will be tan inverse of omega, and for this denominator it will be under root of 4 plus omega square, angle tan inverse of omega by 2. Okay, now if we take this angle into numerator, it will be minus tan inverse of omega by 2. Okay, and if we add both this term into this omega t, it will be magnitude into 100 cos omega t plus tan inverse of omega minus tan inverse of omega by 2. Okay, so here you can see this is our V2, this is our V1. Now in the question it is mentioned that the phase difference between voltage V1 and V2 is equals to pi by 4. Okay, so if we take angle of V2 first, then angle of V1, so it will be tan inverse of omega minus tan inverse of omega by 2 minus of minus tan inverse of omega t, it will be plus tan inverse of omega by 2, right? So this tan inverse of omega by 2, this minus tan inverse of omega by 2 will get cancelled and we will remain with tan inverse of omega. Okay, similarly if we take angle of v1 first then v2, okay, basically angle of v1 minus angle of v2, so it will be minus tan inverse of omega by 2. Okay, here I have taken angle of v1 minus angle of v2. Okay, so here it will be minus tan inverse of omega by 2, then here we have plus, so minus angle of V2 will be minus tan inverse of omega, then minus of minus it will be plus tan inverse of omega by 2. Okay, so this tan inverse of omega by 2 minus tan inverse of omega by 2 cancel and we will get minus tan inverse of omega. Okay, mod of minus it will be positive, so we will get tan inverse of omega equals to pi by 4. Okay, now if we take tan inverse on this side, we will get omega is equals to 10 pi by 4, right? 10 pi by 4 is 1 radian per second. Okay, so our omega will be 1 radian per second. Okay, so the answer for this question is 1 radian per second. Okay, so once again let us see this question. Here in this question the input was cos omega t, basically the sinusoidal form. Okay, so we have used our sinusoidal state analysis wala step. Okay, first step was not to touch this, not to touch this. Okay, then we have converted all the elements into reactance form. Okay, then we have calculated v1 v2. Okay, and then using this statement angle of v1 minus angle of v2 or angle of v2 minus angle of v1, we have seen both the things and we have got the same answer. Okay, that was tan inverse of omega, as if we take the mod we will get tan inverse of omega only. Okay, and then we have got our omega as our 1 radian per second. Okay, so this was all about our phasor sums. Okay. Hello friends, today we are going to see the trick by which we can solve resonance based AC circuit sums very easily, very fastly. Okay, so before we move to the sum, let us see the condition for resonance by which we can identify that this sum is for resonance. Okay, so if in the question it is mentioned that the circuit power factor is unity, or it is mentioned that the resistive voltage is equals to V, or it is mention that your inductor voltage is equals to capacitive voltage, then this question is for resonance. Okay, if it is mentioned that your reactance of inductor is equals to reactance of capacitance, then also that sum is for resonance. If it is mentioned that impedance of the circuit is resistive, or it is mentioned that admittance of the circuit is conductive, then that sum is for resonance. If it is mentioned that your input voltage and input current are in phase, then also this sum is for resonance. Okay, so these are the conditions that will be handy to identify that this sum is for resonance. Okay, now let us see the types of the sums that has been asked in the GATE exam. Okay, you can get the question to find out the resonance frequency, you can get the question to find out quality factor, they may ask about the bandwidth, they may ask about the ratios such as IL by R, IC by IR, VC by VR, VL by VR. Okay, so these are the types of the question that has been asked in the GATE exam. Okay, now let's move on to the concept that are required to solve this type of sum. Okay, so considering that our circuit is in resonance, okay, in series RLC circuit, you will get your resistor voltage is equals to V. If your circuit is at resonance, you will get your resistive voltage equals to V. Your inductor voltage will be equals to JQV. This Q is quality factor whose value is 1 upon R under root of L by C for series RLC network. Okay. You have seen the same thing in the resonance part also, but here we have considered that our circuit is operating at omega equals to omega naught, basically at resonance. Okay, so this formula is only valid only when your circuit is operating at resonance. Okay, so VL will be JQV. If we write in phasor form, it will be QV angle of 90, and if we write the magnitude, it will be QV only. Okay, similarly for VC, it is minus JQV, it will be QV angle of minus 90, and magnitude will be QV only. Okay, so you can see at resonance the magnitude of the inductor voltage and capacitor voltage is same. Okay, and this is the only reason for which your resistive voltage is equals to your source voltage. Okay, as you have seen, your V is VR plus JVL minus JVC. Okay, if your VL and VC is same, so it will be JVL minus JVL, so it will be V equals to VR only. Okay, Quality factor formula is 1 upon R under root of L by C, and the resonant frequency formula is 1 upon under root of L by C radian per second for series RLC circuit. Okay, if you want to write in hertz, so it will be 1 upon 2 pi under root of L by C. Okay, so take note of it. Bandwidth for series RLC circuit is R by L radian per second. If you want to write in hertz, it will be R upon 2 pi L. Note one thing, your bandwidth for series RLC circuit is only function of R and L. It is not the function of capacitor. Okay. Now, as we know, bandwidth can also be written in terms of higher frequency and lower frequency. It will be omega h minus omega L. Omega h is higher frequency and omega L is lower dB frequency. Okay, and this omega h formula is bandwidth by 2 plus under root of bandwidth by 2 ka whole square plus omega naught ka whole square. Okay, and omega L is simply minus of bandwidth by 2 and the rest of thing is same. Okay. And if you want to write quality factor in terms of your resonant frequency and bandwidth, then it is quality factor is equals to omega naught by bandwidth. Okay, this is very handy formula. You should take note of it. Okay, and the last formula that you should know for series RLC network is this one. Okay, quality factor of series RLC network in terms of zeta is 1 upon 2 zeta. Okay, this will be handy whenever we get any transfer function, and from the transfer function we have to get the quality factor. Okay, now let us see the same thing for parallel RLC network. So here this is a parallel RLC network. At resonance, IR will be II, IL will be minus JQI. Okay, note one thing, this circuit is working at resonance frequency. Okay, and this formula is only valid when your circuit is operating at your resonant frequency. Okay, so your IL will be QI angle of minus 90 degree in terms of phasor, magnitude will be QI, IC will be JQI, in phasor it will be QI angle of plus 90 degree, magnitude will be QI only. Okay, note one thing, IL and IC both are same. Here in series VL was JQV, here in parallel IL is minus JQI. Okay, note this thing, positive and negative. Okay, this all thing you can derive from the circuit itself. There is a derivation for this. If you want this derivation, please ping this in the comment box. I will drop the drive link for this derivation. Okay, now let us see the quality factor formula for this parallel RLC network. Okay, so quality factor for parallel RLC network is inverse of series quality factor, so it will be R under root of C by L. Okay, and the resonant frequency formula is same for parallel as well as series, which is 1 upon under root of LC. Okay, this is in radians per second. If you want in hertz, it will be omega naught equals to 1 upon 2 pi under root of LC hertz. Okay, bandwidth is 1 upon RC. Note one thing here, the bandwidth is only the function of R and C, it is not the function of L. Okay, it is in radian per second. If you want in hertz, it will be 1 upon 2 pi RC hertz. Okay, sorry for this, it will be hertz. Now bandwidth is also written as omega h minus omega L. Omega h, omega L formula are same as you have seen in the series RLC network. Just the only thing is here the bandwidth is 1 upon RC, omega naught is 1 upon under root of LC. Okay, and the quality factor in terms of omega naught and bandwidth, it is same. Quality factor in terms of zeta is also same. Just you should take note that zeta, omega naught, bandwidth for parallel RLC network is different as compared to series RLC network, but the formula for omega h, omega L, QP, QS in terms of zeta, omega naught, bandwidth are same. Okay, so take note of it. Now let's start with the sum. This is the first sum. It is of EC 2014. The question is the angular frequency at which the Norton equivalent impedance as seen from terminals B dash to B dash is purely resistive is. Okay, so here in this question you can clearly see it is mentioned that your circuit is purely resistive. Okay, as we have seen in the condition that if we get purely resistive or purely conductive circuit, then it means that the circuit is operating at resonant frequency. Okay, so from this we get to know that we have to get the resonant frequency. Okay, so now let's see the procedure to solve this. Okay, so here you can see this is the circuit from which we have to get the Norton equivalent resistance. Okay, basically we have to get the RTH. Okay, and the RTH procedure is here you can see here we have only independent voltage source. Okay, so this type of question is type 1 of Norton and Thevenin. Okay, so for this type we directly replace this independent voltage source by short circuit and independent current source by open circuit. Okay, so here we are going to make this independent voltage source to short circuit, so this is the modified circuit from which we have to get our ZTH. Okay, note one thing here, in this modified network I have converted RL to j omega L and C to 1 upon j omega C. Okay, this is what we have seen in a detailed fashion while we started our AC circuits. Okay, so our ZTH will be R parallel with j omega L plus 1 upon j omega C. Okay, now let's try to separate our real part and imaginary part. Okay, So if we solve this, it will be r into j omega l, so it will be j omega l r upon r plus j omega l, right? R plus j omega l, and this will be 1 upon j omega c. If we take j to numerator, it will be minus j upon omega c. Okay, now we have the task that we have to separate our real and imaginary part. Okay, so to do so, we are not going to cross multiply it. We are going to rationalize this part such that we will get the imaginary and real part of this term. Okay, so let's rationalize it. So it will be j r omega l r minus j omega l. Okay, so this is what I have written, and at denominator it will be r plus j omega l multiplied by r minus j omega l. Okay, so it will be a plus b multiplied by a minus b, so it will be a square minus b square. Okay, so a square will be r square minus b square, it will be j omega l the whole square. J square, it is minus, so minus minus will be plus, so we will get r square plus omega square l square. Okay, and this term will be same, which is minus j upon omega c. Okay, now if you multiply this term inside this bracket, we will get j r square omega l, and here we will get j minus 1, and this minus minus will be plus, so it will be plus r omega square l square. Okay, so this is what I have written. The real part is plus omega square l square r upon r square plus omega square l square, and the imaginary part, this is what our imaginary part, so it will be r square omega l. Okay, r square omega l upon r square plus omega square l square, and this is the negative wala part, which is minus 1 upon omega c. Okay, as we all know, when our circuit operate at resonance frequency, the imaginary part, basically the reactance of our circuit, will be 0. Okay, so we have to equate our imaginary part equals to 0. Okay, so if we equate it, we will get r square omega l upon r square plus omega square l square minus 1 upon omega c equals to 0. So if we take this term to this side, we will get r square omega l upon r square plus omega square l square equals to 1 upon omega c. Okay, now let's simplify it. We want omega, right? So we will do accordingly. So now before we further simplify, what we are doing is we are substituting our R, L, C value, okay, such that our complication will be reduced. Okay, so R value is 1 ohm, L value is 0.5, and C value is 1 farad. Okay, so if we substitute it, we will get something like this. Okay, now what we are going to do is we are going to take this omega here and we will take this to this side. Okay, so we will get omega into omega, it will be omega square. 0.5 is basically 1 by 2, so omega square by 2 equals to, if we take this term this side, we will get 1 plus omega square multiplied with 0.25. 0.25 is 1 by 4, so we will get 1 plus omega square by 4. Okay, now if we take this omega square by 4 this side, we will get omega square by 2 minus omega square by 4. Okay, so it is nothing but 1 by 2 minus 1 by 4, so it will be 1 by 4 itself. Okay, so we will get omega square 1 by 4 equals to 1, so omega square is 4. So if we take the square root, we will get omega equals to plus minus 2 radians per second. Okay, we cannot get negative frequency, so we will say that our omega will be 2 radian per second. So 2 radian per second is our answer for this question. Okay, now let's move on to the second question. This second question is of EC 2003. The question is, a series RLC network has a resonance frequency of 1 kilohertz and a quality factor of Q equals to 100. If each of RLC is doubled from its original value, the new Q of the circuit is. Okay, so basically this sum is to find out the quality factor of the circuit, and in the question itself it is mentioned that it is having a resonance frequency. Okay, so this sum is of resonance frequency and we have to calculate the Q. Okay, till now what we have seen the first type of question where we have to find out the resonance frequency. Now this is the type 2 question where we have to find out the quality factor. Okay, so for the quality factor we will just use the formula. As we all know, it is mentioned that it is a series RLC circuit. So series RLC circuit quality factor formula is 1 upon R under root of L by C. In the question it is mentioned that inductor is doubled, C is doubled, and R is also doubled. Okay, so if we doubled all this thing, we will get series quality factor as 1 upon 2R. R is double to 2R, L and C is also double to 2, so it will be 2L 2C. Okay, so this 2 got cancelled, and we have this 1 upon R under root of L by C upon 2. Basically our new quality factor is Q old by 2. Okay, so this is what I have written. Q old was 100, so it will be 100 by 2, basically 50. Okay, so this 50 is our correct answer. Okay, so this is the way by which you have to solve this type of question. Okay, now let's move on to this third question. This is also of quality factor where you have to find out the quality factor of series RLC circuit, but this time we have a twist. Okay, here instead of giving the RLC value, here we have given with the transfer function. Okay, transfer function is h of s is equals to 10 raised to 6 upon s square plus 20s plus 10 raised to 6, and this sum is of EC 2004. The options are present here. Okay, now whenever you get this type of question where you have given with transfer function and you have to find out the quality factor, you have to use this formula. Okay, the traditional way to solve this type of sum is you have to take a series RLC network and then you have to convert all the component into Laplace transform, then try to figure out the H of S from that circuit, and from that you have to get your R, LC value, then substitute all those value into quality factor formula, that is 1 upon R under root of L by C. But that method is very tedious. Instead of that, we are going to use this formula. This formula will reduce our stuffs. Okay, so we are going to use this formula. The formula says that quality factor is equals to 1 by 2 zeta. So basically we have to get this zeta. Okay, so here you can see this is a second order equation. So if we compare with second order equation, we all know second order equation is k omega n square upon s square plus 2 zeta omega n plus omega n square. Okay, this is our characteristic equation. Okay, so basically we have to compare the characteristic equation of both this transfer function. So here you can see omega n square is 10 raised to 6. Okay, so omega n will be 10 raised to 3. Okay, if you take the square root, you will get omega n is equals to 10 raised to 3. 2 zeta omega n is 20. Okay, so we want 2 zeta, right? So we will keep 2 zeta as it is and we will take omega n on this side. Okay, so we will get 2 zeta equals to 20 upon omega n. Omega n is 1000, so it will be 20 upon 1000. Okay, now as we all know, quality factor formula is 1 upon 2 zeta. We are having 2 zeta, so quality factor will be inverse of that, so it will be 1 upon 2 zeta, so it will be 1000 by 20. Okay, if you simplify it, 0 got cancelled, you will get 100 by 2, so it will be 50. Okay, so the correct answer for this question is 50. Okay, so from this you can clearly see how easily you can solve this type of question if you follow these steps. Okay, these are very handy method. You should use this method only if you get this type of question. Okay, so let's say this question is also from GATE, and this question says that two series resonant filters are shown in the figure. These are the two filters. Let the 3 dB bandwidth of the filter be B1 and the filter 2 be B2, the value of B1 by B2. Okay, so we have to get the value of B1 by B2 of these filters. Okay, this is one filter, this is the second filter. Okay, if you observe this circuit carefully, here you have capacitor, inductor, resistance value as C1, L1, R respectively, and for this filter it is C2 is equals to 4C1, L2 is equals to L1 by 4, R is same. Okay, so basically in this second filter, just the factor of capacitor and inductor value is increased and decreased respectively. Okay, so you have to do this modification in the formula and you will get the answer. Okay, we all know for series RLC network, here you can see this is a series RLC network and this output voltage is taken across this resistor. Okay, but the circuit is series RLC only. Okay, so you have to use the bandwidth formula of series RLC network, which is R by L. Okay, so here it will be R by L1. L1 value is L1 itself, so our B1 is R by L1. For filter 2, our formula will be R by L, which is nothing but R2 by L2. R2 is R here, so we will keep R as it is. L2 is L1 by 4, so we will substitute L2 with L1 by 4, so it will be R upon L1 by 4. Now this 4 will go to the numerator, so it will be 4 R by L1. R by L1 is B1, as you can see here, so we will get B2 is equals to 4 B1. Okay, now in the question we want the ratio of B1 by B2. Okay, so here we have B2 is equals to 4 B1. Okay, so if we take B2 here and 4 here, we will get B1 by B2 is equals to 1 by 4. Okay, so the correct answer for this question is 1 by 4. Okay, now let's move on to the last question. This question is also from GATE. This is the latest GATE sum. In this sum, we have to get the ratio of mod of IL by mod of IR. Okay, and the circuit of this question is given here. Okay, if you see this circuit carefully, this is a standard parallel RLC network and you have to get this ratios. Okay, as we all know, as we have seen in the basic concept, that IL is minus JQI. Okay, if we take the magnitude, it will be QI. Okay, now let's find out the magnitude for IR. At resonance, IR is I, mod of IR will be I itself. So if we take the ratio, it will be mod of IL by mod of IR, it is equals to QI by I equals to Q. Okay, so basically we have to get the Q value and this Q value will be the answer for this question. Okay, this is a parallel RLC network and the parallel RLC network quality factor is R under root of C by L. Okay, R value is 10, C is 10 microfarad, L is 10 millihenry. Okay, if we substitute it, we will get 10 under root of 10 raised to minus 3. If we simplify it, we will get 0.316 as our answer. Okay, so this is the quality factor as our answer of this question. Okay, we can get the similar type of sum where you will be given the series RLC network and you will be required to find out mod of VL by VR, mod of VC by VR. Okay, so you have to follow the same step and you will get your answer very easily. Okay, so this was all 5 types of sums that has been asked in the GATE exam. Practice it and you will be master of it. Okay, so that's it guys, thank you.